Yeah, thank you. Alright, so good afternoon, everyone. Are there any questions or concerns regarding anything we discussed yesterday? Anything that needs clarification? No, all good. So, assignment 1 has been posted on Piazza, as you may know by now. Those of you who haven't created your Piazza account, please do that, because that's where the assignments are. Right? And it is due on 14th August at 10 a.m. And the reason for that is because 11 a.m. is a drop deadline. So if you haven't done anything by then, it may be not trivial for you to decide whether to continue or to drop. Right? So that's the reason that the drop deadline is 10 a.m. Okay. Anyway, they typically give 10 days, so it's like 9 days. So, okay. Good. Alright, so if there are no questions or concerns, let's get back to where we were. Right? So we discussed these two problems. One is an optimization problem, more specifically a combinatorial optimization problem. You're given a graph and a cost function on the edges, and you want to find the minimum cost perfect matching in this graph. Of course, there is a question that arises. First of all, does the graph have a perfect matching? Right, we have discussed that the graph does not have a perfect matching. But anyways, let's assume that the graph has a perfect matching. Even in that case, this is not an easy problem. Just because the graph has a perfect matching doesn't mean you're going to find one with minimum cost like that. But anyways, we'll also talk about existence of perfect matching and all those things. And related to this is the decision problem. You're given a graph, you have an edge cost function, and you are given a particular perfect matching of the graph. And now the question is the given perfect matching one of minimum cost amongst all perfect matching in the graph? Right? And we discussed that clearly if it is not of minimum cost, then it's easy to convince somebody that it is not of minimum cost by just showing them a better perfect matching. Right? So there exists a certificate. What is a certificate? A better perfect matching. You just show it to them, and now they cannot argue that the original one is a minimum cost perfect matching. So therefore, we say that the problem belongs to, the decision problem belongs to co-NP. That's a complexity class. And if similar thing happens for yes instances, so these are no instances. When the graph doesn't, when the given matching, perfect matching, is not of minimum cost, that is a no instance. So if the same kind of thing happens for yes instances, then you would say that the problem belongs to NP. Okay? So in other words, is it easy to convince someone that the given perfect matching is indeed of minimum cost? Right? And I hope that we all came to the conclusion that it is not as easy as the earlier task. That how do you convince someone that the given perfect matching is of minimum cost amongst all the matches? And here is an example. Of course, this is a small graph. You can just enumerate all the perfect matchings, but that's silly. In general, you will not be able to enumerate all the perfect matchings because there will be too many. So, what we are going to do is we are going to see if there is another way to convince ourselves that the pink colored perfect matching is indeed a minimum cost perfect matching in this graph. And the idea was, one of the ideas we discussed, is I can take any vertex and I can perturb the cost of each edge incident at that vertex by the fixed constant. Let's say I subtract k. The k is a given. Then of course, what happens is, because I am doing this at every edge incident at a particular vertex, the cost of each perfect matching goes down by k. Yeah, you see that? And therefore, a minimum cost perfect matching in the new instance is still a minimum cost perfect matching in the old instance. Okay. And vice versa. So the question is, the DIY was find a set of labels So these are vertex labels. You can think of L as a function from the vertices of the graph to the reals, such that the new instance I'm going to leave some space here. As the following properties. The first property I want is that the cost of every edge in the new instance is non-negative. So the new instance I'm going to call it C prime. We are not changing the graph, so I'm just going to denote the new cost function by C prime. Graph is G. This is my G in this example. So I want all the C primes. I can either write E or I can write UE. It's a simple graph. So for every pair of vertices, if there is an edge, the C prime of that edge is greater than 0 for all UE in the edge set of the graph. And the second thing I want this pink fellow to have cost 0. We all agree that if we can find such labels, right? Everybody sees what we are doing in C prime. Then we are done. Then this n is indeed a minimum cost perfect function. You all agree? So now let's define C prime. I want to directly define it for each edge. So what is happening at each edge? What is the cost of each edge in the new instance? What should I subtract from it? Someone? Yeah?
The minimum cost is there.
Why minimum?
That it remains positive all the way.
No, so remember what we are doing. We have these labels on the vertices, and for every vertex, I am going to reduce the cost of each edge incident at that vertex by the label of that vertex. Right? So can I directly define the C prime of an edge based on this?
And then UV, C and UV would be C UV
Minus the label of U and the label of V. Do you all agree? Yeah? So it's just C prime of UV is simply defined as the original cost of the edge UV minus the label of U minus the label of V. You all agree? This is exactly the same thing. Whether you think from the point of view of vertices or you think from the point of view of edges. Right? That's actually how you do the handshaking number. You just change the viewpoint. You change the viewpoint, you see the handshaking number. So this is our new instance, same graph and new cost function. And according to the new cost function, we should have these two properties. So, was anybody able to find such a set of labels without watching the YouTube channel video? Yeah, Bipartite? Okay, go ahead. I'll take your set of labels. Or do you want to come and show the labels? Up to you, you're being recorded. You know. I'll give you a chalk with a different color. When you put on each vertex the label in yellow. While you do that, I'll make another copy of the same color. Yeah? Thank you. Okay. So the Bipartite has proposed these labels for all the vertices. So let's see, according to this formula, what is the cost of each edge? So can somebody, I don't want to look at two things. Can somebody tell me the cost of this edge? RS. RS. 6. Did I hear 6? 6. SRT. Shout it out. 0. RU. 0. RV. 6. 4. RW 1, ST 0, TU 0, UV 0, PW 1, SW 0. Yeah? I didn't make any mistakes. You made mistakes. If you did. Yeah? All the numbers we have written are non-negative. You are agree? There we had some negative numbers. Now we have only non-negative numbers. And the perfect matching that we had was basically the one containing this edge, and this edge. 0, 0, 0. Yeah? No mistakes, all okay? What is the conclusion? M is indeed a perfect matching of minimum cost in this instance. Yeah? Since such labels exist, for the given instance, by given instance, I mean the original instance, not the new one. And is a perfect matching of minimum cost. Yeah? You're waiting for this exam. Yeah? Okay, the question of course is, the burning question if I may, is whether such labels always exist. This it seems a bit like magic. Whatever black magic department did, I don't know. But seems like some kind of black magic. Anyways. So the burning question. Right? Because if you can prove that such labels always exist, or actually, even if we cannot prove, if they exist, that's what matters. If such labels exist, then we can conclude, or whoever proves it can conclude, that the problem belongs to LP. Right? Because if such labels exist always for any given instance, then for any given instance, you would be able to convince your friend that a given perfect matching is indeed of minimum cost. So the answer to this question, any guesses? Yeah? No, because you did some black magic to find them. Right. So what about others? Do they always exist? Or do people think the way they imagine things, which is quite pessimistic? Right. In this case.
So just to clarify,
Yeah.
so the question is, given a cost matching, whether it's a
Right. Given any instance of this problem, which is a yes instance, and is indeed a perfect matching of minimum cost, can you find labels on the vertex set that would achieve these properties? That's the question. So what do the others say? Do they exist? I'm not asking you to prove it, one way or the other. Yes. Yeah, exists. Exists. No, 1 no, 2 yes. Okay? How many people think they always exist? Raise your hands. How many people think they will not always exist? 1, 2, 3, 4, 5. People. Okay. Turns out the latter group is right. They don't always exist. They do exist for certain classes of graphs. So for some graphs they do exist. Anybody wants to guess which graphs? Wheel. I'm not sure about wheel, but there is another rich class of graphs for which it exists. Maybe wheels also might be. Actually, that's a question I've had on mind. But yeah, I don't know the answer. Bipartite graphs, right? So for bipartite graphs, which I will define, they always exist. In case there are those who don't know what bipartite graphs are. Yeah. So the answer in general is no. In general, but yes, in the case of certain graphs, including the very rich class of bipartite graphs. So that means if the given graph is bipartite, then the problem is an NP. Right? So if I promise you that the input graph is bipartite, let's just write it down. I call this EP main clause bipartite perfect matching. I haven't defined bipartite, that's okay. I'll come to that. Given a bipartite graph, G cost function C from the edges to the reals and a perfect matching N decide whether N is a perfect matching of minimum cost. So of course, by the previous discussion, this problem belongs to co-NP because it belongs to co-NP for all graphs, of course for multiple graphs. But because of this answer, yes, in the case of bipartite graphs, this problem also belongs to NP. Right? So for any yes instance, there is a certificate, a set of labels that I can give you and convince you that the given perfect matching is indeed of minimum cost. Right? And not only that, generally speaking, in graph theory and combinatorial optimization, typically when a problem belongs to NP and to ONP, in most cases the problem also belongs to P. So it also belongs to P. You can actually find these certificates efficiently. And if you don't care about certificates, you care about optimization, then it also implies that this problem, the optimization problem also belongs to P in the case of bipartite graphs. So if you assume that the input graph is bipartite, then the problem will actually efficiently solve this. Turns out, all these complexity theoretic statements I am making, they are actually true for all graphs, not just bipartite. The problem is that if you want to deal with all graphs, the certificates are more complicated. Just a set of vertex labels does not work. In general, when it comes to matchings, which is actually my own research area, when it comes to matchings and perfect matchings, there is generally a long gap between solving the bipartite case and solving the general case. The gap generally ranges between 10, 20 to 50 years, and in some cases, there are problems that are solved for bipartite graphs that we still don't know how to solve for non-bipartite graphs. So, yeah. So, the world of matchings is a world where you see a very clear dichotomy between bipartite graphs and general graphs. So we will prove in this course that yes, they exist in the case of bipartite graphs, and we will also see the more complicated certificate or more sophisticated certificate that exists in the case of non-bipartite graphs, and that will also be a consequence of things you will see in the course. So we will actually conclude that even for the general case, the answer is yes. And this is because of Edmonds 1965. Okay? Well, the bipartite case is actually much older. Generally, it's called the Hungarian algorithm. The Hungarians have figured out many things much before the non-bipartite case was solved. Okay. But now that we are talking about LP&CO and LP&P, I also want to address another elephant in the room, which is, does a given graph have a perfect matching? And that is something we haven't talked about. So that's another problem I want to talk about. This is not really so much of an optimization problem, and it can be viewed as one. So DP, PM. This is a more basic question. There are no costs on the edges. You just have a graph, and you have to decide whether the graph has a perfect matching or not. Right? Because if you're going to find a minimum cost perfect matching, well, you should first find a perfect matching. So, I did not go here deliberately because I wanted to focus on optimization. Okay? But I'm going through this as a second step. Given a graph G, decide whether G has a perfect matching. And how do you decide this? Again, costs. Let's say it was something more basic. If you want an optimization version of this problem, we need to define one more concept called maximum matching. So let's talk about maximum matchings. So let's draw a graph that does not have a perfect matching. Let me know. This has 5 vertices. Does this have a perfect matching? It does. Okay, annoying. Okay, this one doesn't have a perfect matching, right? No, it still does. Okay, now it doesn't have a perfect matching. Can anybody find a perfect matching as well? I don't think there is one, but I did not check carefully. If you find one, let me know. In the meantime, I'll start labeling the vertices. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It has 10 vertices, 0 to 9. And does it have a perfect matching? Can we found it? No, nobody found it. Okay. So the question is, how do you convince somebody that there is no perfect matching? What about this graph? Does it have a perfect matching? Yeah. Yeah, you see it? How did you convince yourself? By finding one, by observing one. So what does it mean? For this problem, is it an NP or co-NP? NP. You are agree? It is easy to convince somebody that a graph has a perfect matching. Throw a perfect matching at them. Right? So clearly this problem belongs to NP. The certificate is a perfect matching. What is not immediately clear Why should this problem belong to O and P? How do you convince somebody that a given graph does not have a perfect match? That's not so clear, right? You see the point? Okay. But let's talk about an optimization problem. This one does not have a perfect matching, but maybe it has a big matching. Maybe not perfect, but as big as possible. Can somebody find a matching that is as big as possible amongst all matchings? Right? By big I mean number of edges in the matching. So how big is the matching you can find in this graph? 4. And perfect matching would have how many edges? 5. You are able to find one with 4. So if you believe that the graph does not have a perfect matching, then the matching of size 4 has to be as large as possible. So I guess here is one. Yeah. Here is the matching of size 4. Cardinality of M is 4. But you all seem to believe that this graph does not have a perfect matching. Therefore, if that is true, then this should be a maximum matching. So maximum matching is a matching of maximum cardinality. Right? So it's clear? Any matching that has largest cardinality amongst all matches. Okay. And now you can ask the optimization problem. Given a graph, find the maximum matching. So now there is no cost, or if you like, the cost of each edge is equal to 1. Right? Now, earlier I talked about perfect matching. Forget it was. Okay. So the optimization problem I want to talk about is this one, OP max matching. Given a graph G, find a maximum match. A graph that has a perfect matching, the maximum matchings are exactly the perfect matchings. You all agree? Observe that. It's an easy observation. If a graph G has a perfect matching, then perfect matchings of G are the same as maximum matchings of G. Yeah? Do you agree with that? So in general, you can ask a question. You can generalize these questions. Supposing your graph does not have a perfect matching, you could ask for a maximum matching of minimum cost or maximum cost. It really doesn't matter. So you can ask these kind of problems. Turns out that for all these problems, in some sense, you can just restrict yourself to the perfect matching problems. If you solve those, there is a way to solve the maximum matching problems. I won't go into those reductions too much. So that is one reason why we will focus a lot on the min cost perfect matching problem. Because all these max matching and other kinds of variants, they can actually be reduced to perfect matchings using some gadgets. So I'll just skip that part for now. If there is time, we might talk about it later. But what I want to talk about now, I want to talk about this problem. given a graph G, decide whether it has a perfect match. Right? And again, we will focus on the so-called bipartite case, for which I will first define what a bipartite graph is. And we will try to see why this problem is actually the bipartite version. It is actually NP. It's actually true for all graphs, but that I'm not going to talk about today. That's more complicated. I don't want to really talk about it right now. So, okay, so how many of you have no idea what a bipartite graph is? Can I get some show of hands? Never heard of bipartite graphs? Anyone? Okay, so then can I get a show of hands to define bipartite graphs? Anyone who's define bipartite graphs? Okay, David.
There exists a partition of vertices
Right.
in two sets such that every edge has its endpoints in different.
Right. Partitioning to two sets, right? Okay. Yeah. So, let's do a quick example. What Neeraj is saying is, you can partition the vertices into two sets. So you have 8 vertices. You can partition them into two sets. Let's call them pink and blue. Why not? So the pink vertices and the blue vertices. And every edge has to go from a pink vertex to a blue vertex. Is that correct? So can you color, if I may, the vertices of this graph using two colors, pink and blue, so that every edge goes from a pink vertex to a blue vertex. Yeah? Do you see a way to do it? Yeah, just start at some vertex. And if this color is pink, the neighbors of this color have to be blue. And now the neighbor of this color has to be pink. This color has to be pink. This color has to be blue. And this color has to be pink. And it looks like you were able to do it. Every edge is joining a pink vertex to a blue vertex. Therefore, this graph is bipartite. So I won't write down the definition. I will just write down bipartite graphs are the same as two colorable graphs. Right? And I think this says everything you need. Okay. So these are exactly two colorable graphs according to this definition of coloring. Okay. So the standard way of drawing a bipartite graph is these are your two vertices, these are pink vertices. That is, if you are me, if you are an algorithms person, you make it vertical. For some reason they like this, but I like this. We all have our eccentricities. Okay. So that's what a bipartite graph is. And now what I want to do is I want to discuss this decision problem restricted to bipartite graphs. Right? We can already see the problem belongs to NP. You just show a perfect matching. Why does it belong to co-NP? And some of you would have seen this in your earlier courses. And for those of you who haven't seen it, let's make sure we are on the same page. For a bipartite graph, I will often use the notation G square brackets A, B to denote the colored classes A and B. Yeah. So, given a bipartite graph, G with color classes A, B. So I've already given you fixed color classes. Of course, there may be multiple ways to color it, which actually happens when your graphs are not connected, but whatever. I've already given you the color classes, the pink vertices and the blue vertices. Decide whether G has a perfect matching. Right? So as we discussed earlier, clearly the problem belongs to MP. The certificate is just a perfect matching. But it turns out that this problem also belongs to OMP. We will not prove this because this is supposed to be proved in a previous course, so we are just going to discuss it without proof. If you are interested in a proof, you can go check out my YouTube channel and stuff. So how many of you have seen this material before? Something like a bipartite graph is a perfect matching if and only if blah. Okay, raise your hand if you have seen it. 1, 2, 3, 4. That's it? 4, 5. Okay. Okay, fine. So it's called Hall's theorem. Now does it ring a bell? How many of you have seen Hall's theorem before? More hands. Slightly. Okay. So let's discuss some obvious conditions under which a bipartite graph may not have a perfect matching. Can anybody think of an obvious condition? I have a bipartite graph with blue vertices and pink vertices. Can you think of one very obvious reason why this graph would not have a perfect matching? Like as basic as it gets. Disconnected. Is that really a problem? Can you draw a disconnected bipartite graph that has a perfect matching? You can. Draw it. Number of vertices being odd, that is always a problem, right? Bipartite or not, that is true. So the number of vertices is odd, definitely there's a problem. Can we make it stronger? Something to do with pink and blue? One partition has more vertices than the other. So at the very least what you need is you need the number of blue equal to number of pink. Yeah? So that much we need for sure. So necessary conditions for existence of perfect matching. So definitely you need the number of pink vertices to be equal to the number of blue vertices. Is that enough? I'll draw two graphs. Here are two graphs. Each of them have 5 pink and 5 blue vertices. This is my graph G1 and this is my graph G2. See if you can find, do it now, right? Which one has a perfect matching, which one doesn't have a perfect matching? Draw them. And maybe both of them have perfect matching, maybe neither of them has, I don't know. I mean, I do know, but anyways. And if you can't find a perfect matching in one of them, then convince your neighbor that one does not exist. And then try to figure out how you convince them. If you want to label the vertices, you can label them 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, for the lack of creativity. So the same thing there. Could I redraw G1? Some things are not very clear. Let me make them clear. This is an edge. So basically what you have, so this part we can just make it clear. Yeah, now is it clear? Okay? So then you put by imagination. Yeah, clear? Yeah. Okay? So, do both of them have perfect matchings? Or does one of them not have a perfect matching? One of them doesn't have one. Karthik, which one? G1 does not have a perfect matching. Yeah, does everybody agree? G1 does not seem to have a perfect matching, whereas G2 seems to have one. Right? And you convince yourself by showing one or finding one. Small example, you will find it. Right? Okay. So let's do that. G2 has a perfect matching. I don't know. Something like this. In fact, I think G2 has many perfect matchings. And yes, G1 doesn't have a perfect matching. How would you convince your neighbor or yourself for that matter that it doesn't have a perfect matching? Does anybody have a nice convincing argument? Preferably someone who has not seen house sale before. For those who have not seen house sale before, yeah, not seen house sale, go ahead.
We can partition G1 into two vertices of all vertices.
Okay.
Then the number of vertices becomes 0. In that partition is 0.
Oh, I can do that here also. I will add one, there's a partition to one, odd on the left, odd on the right.
Yeah.
I will add one more edge. Then the number of edges will be even more. That doesn't work, right? I can do that if it has a perfect match. So, I'm glad that you're looking at this partition, right? This is a partition you're looking at. So that's a good partition to look at. But do you really care about the partition? Or do you care about something more fundamental in those parts? Okay, somebody else has a hand raised. So, yeah, go ahead.
G1 on the, if you look at the left part,
G1, the left part.
Yeah. So 5, 6, and 7. All three of them are connected to 0 and 1.
0 and 1. Right.
So-
Right. Yoshidas, right?
Yeah.
Okay.